In this video, what we're going to do is we're going to look at using MultiSimLive, which is the online version of Multisim, to verify our power factor and to verify our power factor correction, just using the oscilloscope facility in there essentially. So the first thing we want to do is we want to build a circuit that emulates or mimics what we have in our system. So if we're looking at a motor or a contactor or whatever it might be, whatever the component is, we're just going to build a circuit that takes the component, represents it as a resistor and as an inductor. Okay, so firstly what we're going to do is we're going to grab some values. So these are the values that we're going to use here to build our circuit. Okay, so we're going to have a resistor in there that's 80 ohms. We're going to have an inductor that's 700 millihenries, a voltage supply of 24 volts at a frequency of 50 hertz. Okay, so just on Multisim. So once you need to go to multisim.com up here. If you haven't already done so, you'll need to create an account with them. And then once you've created your account, you'll come back to this page here. And from this page here, we're going to go to Circuits and My Circuits. And then in here, we can create a circuit over here. Okay. So this is going to allow us to build the circuit and then run the oscilloscope page, which they refer to as a grapher in this particular software. Just takes a minute to initialize there. Now, because this is the free online version, we are limited in what we can do, but there is enough in here to be able to create an RL circuit and be able to put a capacitor in there to be able to see the power factor correction. So just a quick tour, I suppose, of the software itself here. So we have an untitled circuit up here. So we'll just, that's where we can put in our title. Oh, sorry, I was supposed to be typing up there. There we go. So we're just call it power factor correction. Okay. Now the asterisk beside it means that we haven't saved it. So if we go over here, we've got the little 9-dot matrix here. So if we click on that, we can save as if you haven't already named it. So there's power factor correction, and we can just click OK. In the free version of the software, I don't think you're allowed to create private circuits. They're all public circuits. Okay, but that's not an issue for us anyway. I've also dropped in a resistor there that I didn't mean to drop in. So that the 9-dot matrix here is where we can create new files, we can stream, we can export it, or we can navigate around different parts within the software here itself as well then. Okay, then just below that then we have the information here, which gives us information on the project. That tab can change depending on what we've selected around the board. We have the run simulation, or the play button here, and then if that's active, the stop button here will be active. Okay, we can change, as with any other signals, we can change how we present the signal. Interactive is what we want to do here, let it run. And then these are the different windows, I suppose, that we have. We've got the schematic, which is this page here where we can build our schematic. The grapher is the oscilloscope. It says waiting for data there. And then the split then is just a split screen between the two of them, which is, I suppose, once we built the circuit, is probably the more useful one to be using. Okay. And then to the right hand side here then we have the gear wheel. This will give us settings dependent on which window is active here. So at the moment here it's just a document window because we've selected this. If I click on the oscilloscope screen here, or the grapher screen, you can see it changes to plots and axes and stuff, and we'll look at that a little bit more when we have something in here to work on. Okay. Down the left hand side then here is our components. So this is the components that we can use to build our circuits. There's, as I said, lots of circuits we can build in this, but I think it's 5 or 6 components that we're limited to due to the fact that we're using the free version. Okay, if you want to use a paid version, that is obviously then unlimited. What you might find useful as well is there are some public circuits in this software. You can go back out to MultiSimLive. We'll just save those changes before we go anywhere. Okay, and you can search out here for circuits. So you can go to public circuits and stuff. You can search here, and even if the circuits are bigger circuits, you can still go in and you can still emulate them. It's just that you won't be able to edit them. Okay, but you will be able to edit them. So I'll just go back in there to my circuit and open circuit again because I closed it there. And there we go. Okay, so I'm just going to go to the schematic here, just to give that the full screen here for the moment, so that we can work on it. There is a zoom in, zoom out here as well that we can use. Okay, so we want to build our circuit. So as I said, down along the left hand side, here's where all the components are. First thing we want is a power supply. So we click on the sources there. We want an AC voltage. So we just click on that and we'll just pop it onto the circuit there. Once we've popped it in, we can duplicate it, we can delete it, we can flip it or rotate it. Okay, and you can see it's got some values on it here as well. We'll come back and we'll change those in a moment and we'll set that up. Okay, but for the moment we'll just keep dropping in components. So the other thing we're going to need in here is a resistor. So we'll just drop that in, we'll pop it there. Okay, and then we will rotate that to have it vertical, and then go back to the passive components here, and we'll get our capacitor as well. We're going to pop this in. I'm going to have the capacitor here in the circuit, but what we will do is we will put a switch on it, so that we can actually switch it in and out of the circuit, so we can see the circuit with the capacitor for power factor correction and without the capacitor for power factor correction. Okay, and I'm just using the grid here to line these components up, if they work with me. There we go. And as I said, we're going to get a switch here. So just down here, we've got switches, single pole, single throw will do me. And we'll just rotate that around until we get it in place there. Okay, so there's the components that I need. I haven't put the values on them yet. We'll put the values on them in a moment, but what we're going to do is just going to connect them up first. So if you've used Multisim, the full version, it's very similar here. When you mouse over any of these diamonds here, you'll see that get that little connector icon. Okay, so we can just left click on that. We can go up here, and if we left click, it'll give us an angle or a corner, and then we just come down here, and when you get to a connection point, you can see that circle. So once you're there, you just click on that, and that'll give you that line there, and then we can just continue to click away and create our circuit. Alright, and again, we can just left click anywhere just to give us the angle on the circuit, or just a nice sharp corner. Alright, and then we can go from here and we'll go up to there, connect these two components, and then finally connect this one down here. Right. Now that circuit should be operational and it should work for us. We will, however, get a warning with it, and we can get some erroneous values, shall we say, if we don't actually earth the negative side here, or the neutral side of the AC supply. So we do need to go up here to the schematic connectors and get a ground connector and just tie it in down here to the zero side of that. Otherwise you will get some erroneous values, as I said. Okay. So just as a reminder, these are the values we're working with. So the resistor is 80 ohms, the inductor is 700 millihenries, 24 volts at 50 hertz for our supply. So let's pop those in. So any components, we just double click on them. It opens up this properties window on the right hand side. Okay, so the first thing is we don't want peak voltage here. We're going to go for RMS voltage, so we'll change that. And our voltage then is 24 in this example, and our frequency here is 50 hertz. Okay, we can put in phase offsets and stuff, but we don't need to do any of that. We're happy with that. Okay. So we change the resistor here. So again, just double tap on the resistor, and we can change that just to 80 ohms, right? For bigger resistors, if it was 80,000, we'd just put in K in there for 80 milliohms, if there was such a one. We'd put a small m in there so we can put the different values in there. And the inductor, we're going to change that, and ours was 700 millihenries, so we'll put 700 M. And I leave the capacitor alone for the moment. I won't change the value on that because I don't want to ruin the surprise of what we're doing a little bit later, shall we say. Okay, so we've got a power supply set up. Now if you remember, this resistor and this inductor, they're representing whatever component we're trying to do the power factor correction on. So whether that's a motor coil, a contactor coil, a relay coil, a lamp, whatever it might be, a factory. Okay, we have the resistance value and the the inductance value of the system. Okay. Now what we want to do is we want to be able to plot the voltage against the current. Okay, that's what we want to do. We're going to plot the voltage against the current on the grapher or oscilloscope. So if we go up here, the top of the top one here on the list of components that we have are our probes. Okay, so we want voltage, so we're going to click a voltage probe, and we want to look at the supply. So we're just going to put it up here at the top. Again, where you got that circle swinging in there just to show you're connected. If this isn't connected, if you haven't connected it properly, you'll see you don't get the fill in it. It's an empty fill. So it's only when you actually have it on the circuit it fills in a color. Okay, now these are color coordinated, so I'm going to grab current here. They're all green when you put them in here, but if I pull the green one in here, or the current one in here, you see it goes blue. These are color coordinated then to the grapher, so the traces will be green and blue in the grapher. Okay, one thing just to be careful of with the current one, there is, just, we can zoom in a little bit here, there is an arrowhead on it to show you the direction of current flow. Now AC, the current will be flowing in both directions, but we know in order to be able to do our calculations we have to set a reference, and we've done that in the supply here, given a positive and negative on this side, so current will be flowing in this direction for our reference. If I take that probe and I put it over here, you'll see that the arrow is in the other direction. Okay, that will make a difference to us in our plot because our sine wave will be 180 degrees out. Okay, so we just want to make sure that we do have that arrowhead flowing in the right direction. Those numbers that you're seeing here, there's a 1 up there, there's a 2, 4, a 0. They're the nets as they're described in SPICE circuitry and stuff. It's just showing the network and the connections, and they're numbering them. Okay, so that's our circuit built essentially. Okay, what we want to do now is we're going to do a split screen here. Okay, so we can bring up the plot here. Just get this set centered on the screen so we can just keep an eye on him. Okay, now if I just hit the run simulation or the play button over here, okay, you can see it loads the simulator, and then my plot has come in here. Now you can see it's all over the place, as most oscilloscopes readings are until you actually set them up. Okay, so there's a few things we need to set up here from the oscilloscope point of view. We've got to set up our vertical axis and our horizontal axis. So the horizontal axis is the time. Okay, so if we just we're in that gear wheel again here, so if you select this screen, select the gear wheel, it pulls up the properties for the oscilloscope or the grapher. So the first thing we'll do here is trigger it, so we'll just give it a normal trigger. Okay, and that should trigger on a signal here. We've got a rising edge here, and PR1 is probe 1, okay, which is voltage. So you can select either the voltage or the current probe that we have there. You can see up here on the plot it's PR1, PR2. Again, color coordinated to the probes on the left hand side. We've got solid and dotted lines and stuff like that as well. Okay. The other thing here then on the plots, we can say which ones we want to show and which ones we're not showing, so we can switch them on and off if we want to. Cursors we shall come back to, and then down here then we have the axis. Okay, you can set up values here for the axis manually if you want to, for the two vertical axis. All right, so first one we want to do here is the horizontal, so the time per division is the horizontal. All right, so we're want to move that out there to about 5 milliseconds per division. Okay, and what we're looking for, as with any scope, as any signal, we're looking for, when we're looking for that repeating signal, 2 peaks, 2 troughs at a minimum, so that we can see the cycle on it. Okay, so we can see the current here. Okay, now on the plot that we have here, we have the voltage on the axis of the left hand side, and we have values on that, and then we have current on the right hand side and values for that. So we have 2 scales on this, one on the left, one on the right. So if we click on the voltage down here, so on the axis click voltage, it'll auto range the voltage for us. And so we've got an auto range on the voltage here. We're looking at the peak voltage there of about 34 volts, which we know is an RMS voltage of about 24. All right, and then if we do the same for the current, we can auto range the current. All right, now it does look like in this when it's represented like this now, that the current is greater than the voltage because of the plot. But don't forget, the voltage is plotted against the left hand axis, so we're looking at 10 volts, whereas the current is plotted against the right hand, so we're looking at what, a peak there of just under 150 milliamps. For this particular exercise, where we're looking at the power factor and the phase shift due to the power factor, we're not worried about the amplitude, and the bigger amplitude we have in both signals, the better chance we have of getting a more accurate reading, I suppose, on the phase shift between the two of them. But that's what we have on the plot here. We have the phase shift. Okay, so if we remember with the inductor, in the inductor the voltage leads the current. So the voltage is the green one. So if we look at the voltage here, it's going negative through 0 here in time, and then after that in time, the current goes negative through 0. Right? So we can see that the current is lagging the voltage, or the voltage is leading the current, depending on which terminology we want to do. And what we want to do now here to check the power factor is we want to measure the difference between the two phases here. So what is the shift in the phase here? The measurement we will do on this is a time-based measurement. Okay. So we're going to measure the time difference between the two phases, and then we're going to convert that to the angle, and I'll show you how to do that. But the first thing we want to do is measure it. So to measure it on the scope here, we're going to need the cursors. Okay, so cursors are little measurement tools on the scope. Down here at the moment it says type none. We're going to change that to x-axis, because we want to measure along the x-axis, and you can see now we've got this C1, C2. We've got our two cursors here. Okay, so C1 is tracing along the green trace there. Okay, and you can see that over here, cursor 1, PR1, or probe 1, and it's the voltage. What we want to do is take that and bring it to, so we want to check 2 points on both waves that are the same. Now you can see as I move it left and right here, actually we'll just go full on the graph here for a minute for this piece. As I move it left and right, there's a little step in it, so it is snapping along there. So what we want to do is we want to bring it as close to 0 as possible. Okay. Now when we turned on the two cursors, down the bottom of the screen here, we've got all this information. So the first piece of information we have here is cursor 1. It gives us the horizontal position, which is 10 milliseconds, and then it gives us a vertical reading. So it's that, where is it intersecting the curve? That's what it's giving us here. We want to bring this value here as close to 0 volts as possible. Not always possible with this to get to 0 volts, but we get as close as we can. Okay, and we just have to play with it for a second and see, and just keep an eye on it. So I think there is as close as we're going to get. 71 millivolts. We're not far off. Okay. What we're going to do now is take the second cursor. So we just click on that to select it. We're going to change this to follow the current trace, or probe 2. And you can see the cursor's gone blue now as well. All right, and we're going to bring it along here, and we want to find where that gets as close to 0 as possible. All right. So I'm going to hold it just about, I think I can get it a bit closer. There. Okay, so we're at 400 microamps here now, so that's pretty close. Now, we're not going to, or well, it's very hard to get exactly 0 on those, and in this particular software there's no way of setting it to 0. Some softwares you could put a 0 value in there and it would snap to the 0 point. It's not possible on this software. So a couple of things we want to do. We want it to be as close as possible to 0 for both of them. Okay, and for most cases we'll also want both of them to be at the same side of 0. So what I mean by that is we've got plus 71 millivolts there on the voltage, so we should be on plus on the current. Otherwise we're opening that gap a little bit more, so we want to stay on the same side of 0, so either 2 negatives or 2 positives. Okay, now if I can get, let's say on the current one here, the closest, let's say I can get to the current is minus 50 microamps, just if it was. Okay, that's a good bit closer than the 400. Okay, so in that case it might be worthwhile to have a positive and negative, but in general we want 2 positives or 2 negatives. Okay, so we've set both of these up as close as we can to their 0 value, and then the one we're interested in now is this delta x here. The delta x is the difference between the two of them, and at the moment the difference between the two probes is 3.89 milliseconds. That's the value that we're going to use to do our calculations and figure out where we are. All right, so I'm going to just go back to my notepad here for a second. So we're going to just throw in some calculations for you here. Oh, okay, so some calculations. Okay, so I've done these already, so that you don't have to worry yourselves about it. So given the inductor that we have and the frequency that we are looking at, I have calculated that our inductive reactance is 219.91 ohms. Okay, and if I take that inductive reactance in this particular system where I've got an inductive reactance of that and I have the resistance of the 80 ohms, I can calculate the phase angle. So the phase angle that we have is 70 degrees. All right, and then one last calculation that we'll throw in here for now. A phase angle of 70 degrees will give us a power factor of 0.342, which is a pretty poor power factor. Okay, but I suppose for this, what we're trying to do here, it's the angle is what we're looking at, the phase angle, that phase shift. Okay, so using the scope, we can use a ratio. So on the sine wave, I suppose let's talk about that for a minute. We know on a sine wave that going from 0, positive, negative, and back to 0 again, that's 360 degrees across the sine wave. Okay, and it doesn't matter what the frequency is, one full sine wave is always 360 degrees. Okay, so what we want to do is measure what portion of 360 degrees is this angle here. Okay, so the way we do that is we can measure the time to here. All right, or well, we should know the time to here. So the frequency is 1 over time, the cycle time. So we have a 50 hertz frequency here, which means our cycle time is 20 milliseconds. Okay, and it's just ratios from there then. Okay, so if I just grab this little guy here that I've written up for you. Now we pop it in. There we go. Okay, so this ratio formula that we have over here, this is the key to what we want to do. This guy here. Okay, so what we're doing here is we've got the phase angle over 360 degrees. That is equal to the phase shift time, the time difference between the two phases, over the cycle time. That's what we have here. Cycle time, time difference between the phases, and the phase angle is phi up here. Okay, so we can use that formula then to calculate what our actual angle is that we're seeing on the scope there. Right. So to find, just change that back to a black pen there. So to find the phase angle, we take this formula here, so phi is equal to, we just manipulate that formula and we bring up the 360, so we'll have 360 times t over large T. So that's our formula there. So for our example that we're doing here, we will have 360, okay, and just to explain, this value T here is from the scope. That's the value we're reading off the scope. This delta T value we have down here. So in this particular case here, it's the 3.89. That's what we're looking at for this one. Okay, so we just put that into our formula here. So 360 by 3.89 over, and we said that the T here is equal to 1 over F, which is 1 over 50, which is equal to 0.020 seconds, or 20 milliseconds. Now if I go back here to the delta T again for a second, just to confirm, so down the bottom here our delta T is in milliseconds, so we put that in milliseconds, so we can put this value here in milliseconds as well. Okay, so now we have our two values in milliseconds, and we can grab a calculator here now. Give me 1 second. It's the 360 by 3.89 over 20. So we have a fraction 360 bracket 3.89 over 20. Okay, so our value there is 70.02. So our value on that, our angle there is 70.02 degrees. Okay, and that is to compare with the phase angle that we calculated up here of 70 degrees. So you can see we can be reasonably accurate with it. It is one of those ones, just depending on how close we can get to zero with those cursors, we can get nice accuracy in it, or we might be out a little bit. Okay. So far what we've done is we have created the circuit here in Simulink. I'll go back to the split screen here on this one. So we've created the circuit here on Simulink, on Multisim, sorry, and we've set up the scope, and we've measured the two traces, the current and the voltage, and then we've got that phase shift between the two of them measured in time. All right. The next step then would be, now that we have that system, would be to go away and to calculate, right, given the new power factor that we need, to go away and to calculate what a capacitor would be required in that. Okay, so we're going to be looking at we just grab the old back to the notepad here, and we'll scroll down a little bit. We're looking at a new power factor of, we call that PFN, of 0.95, our classic one that we want to recalculate back to. Now again, I've done the calculations off screen for you. So the capacitor required for this in our system is C is equal to 11.24 microfarads. So I've done the calculations to correct this new power factor, and I need an 11.24 microfarad capacitor to give me the power factor of 0.95. Alright, so back to Multisim, and we'll go back to the schematic here on its own for a moment. And we can leave that open. So we've got our capacitor here, and we want to now set up the value on this. So we just double tap on that and check our value again, 11.24 microfarads. So we put that in here, 11.24, and just U on the keyboard gives us the microfarad symbol. Right, so that's our capacitor set up here now. Now our capacitor, we've got the switch on it here, so our capacitor is not switched into the circuit. Okay, so when we close that switch, we'll switch the capacitor in, and that's when we should see the correction in the power factor. All right, so looking at it as we have it here now, we'll just take away the properties there for a second. So you can see the two traces. Okay, now when I click on the switch here, the green trace won't do anything, but the blue trace will change. Okay, it'll get smaller, and the phase shift between green and blue will change. Okay, so I'm just going to click on the switch over here, and it closes. Okay, so you see it's dropped here, and you can see where it crosses the zero here has shifted away from this cursor back closer to the voltage. We've brought the current and the voltage back closer together, and that is the goal in power factor correction, is to do that. Okay, so what we do now is we just take this cursor here, and we're just going to slide it back, again looking at the value down at the bottom of the screen, until we can get that as close to zero as possible. Okay, just 1 milliamp, we might get it close there, minus 600 plus 300. That looks pretty good. Okay, again, remember, try and keep them both positive or both negative, whichever gets you closer. All right, now in this case, we can see down here, that our delta x, we've changed our delta x, and we're down at 971.62 microseconds now. Okay, you will see the value on the current here change. It's going to change a little bit. It's the capacitor charging, sort of, and a few other things happening in there like that. That will settle in a couple of minutes. Okay, but we're still as close as we're going to get to it. Okay, you can see we're getting a little bit closer to zero is actually where we're going. Okay, without moving the cursor. The cursor's not moving here, it's just the value is changing very slightly. But we'll take the delta x here now. So our new time here now is 971.62 microseconds. So our new time is 971 point, what was that, 62 microseconds. So don't forget, we've got microseconds here this time. We were using milliseconds the last time. So again, so to find the new phase angle, okay, which we will call phi n, phi nu, it's the same formula again. Okay, so phi nu will be equal to 360. This time though we're going to be using t nu over 20. Oh, sorry. We'll leave that as t. So that t doesn't change though, because it's the same sine wave, it's the same frequency, it's the same time period. Okay, so we just put our values in here, and again we just have to be careful now because we've got microseconds and milliseconds. I'm going to bring them all to seconds, so it'll be 360 by 971.62 by 10 to the minus 6 for the microseconds on top, and it'll be 20 by 10 to the minus 3 for the milliseconds on the bottom. Okay, and then we will pop up the calculator again, and he still doesn't want to play ball, so we will do clear that, AB 360 bracket 97, what did I have there, 97162, 971.62 by 10 to the negative 6 over 20 by 10 to the negative 3. Okay, and we're getting 17.79. Sorry, 17.597. Okay, so that is equal to 17.597 degrees. So that is the angle we're measuring between the two phases. Okay, our new power factor is equal to 0.95. Right, so that means that phi nu, the new angle, if we calculate it using this, is the inverse cos of 0.95. Okay, so if we do that on the calculator, we just tidy up that 5 there a little bit, and we put that on the calculator. The inverse cos of 0.95 is equal to 18.195. It's 18.195 degrees. Okay, so in this case here we can see we're a little bit out. If we did a little bit of rounding on that, we would be 18.2 versus 17.6. So we're a little bit out there in our angles in this. Okay, what can we do to improve that a little bit? So what we could do is we could go back here and just go on the grapher screen, and we can put up the properties, and we could bring out our time base a little bit. All right, sorry, this way. So we can do that now, and now we can move the cursors again, and it might give us a little bit more accuracy on it here this time. We might be able to snap a little bit closer. So 71 millivolts is as close as I'm getting there. And on the current, then getting 37, 160 was good there. Minus 56 is close as well. We're going to go minus 56 there. There we go. Okay, and the reason I'm doing that is because I just spotted there that I'm either minus 71 or plus 71. So if I go back to the minus 71 here, there we go, minus 71. So we've got 9721. Okay, as our time there now. So where were we? We've got, tried to get a little bit more accurate, and we've got 97921. 979.21. Okay, so if we pop that into the calculator, we'll see if we get a little bit closer. So it's clear that, AB 360 by 979.21 by 10 to the minus 6, because it's microamps over 20 by 10 to the minus 3 milliamps, and that's giving me 17.63. and we had 17.6 here, so we're not getting a whole lot closer. Okay. Now there would be a little bit of inaccuracy, obviously, when we're measuring it here. The capacitor and our calculations for the capacitor, it might be 11.243159. We might need a little bit more detail there, a little bit more accuracy within the capacitor we put in there to get a more accurate result. Okay, but with a calculation like that, we're well within the margin of error. Okay, and more importantly, we can see the theory behind it and how to do it. Okay, so that's Multisim, using it to show power factor correction. And again, we can just zoom back out here, or zoom back out. We just reattenuate our time scale here, so that we can see the two waves. All right, and again, we can just open and close the switch here, and you can see the correction happening. All right, so we're reducing the current, the supply current, which is what we're trying to do, and bringing that phase angle nice and tight together again by putting that capacitor in. All right. Last thing to do then before we finish up is just to hit the stop button here on the simulation, so we don't leave it running, and then just go to the 9 dots again and click save. All right, and it'll just save it for us, and then we'll have it. Okay. Thanks for watching.